All right. Good afternoon, class, or good morning, whatever time it is when you're watching this video. This is our day 5 lecture. So I'm going to go ahead and share my screen as we get started here today. This is our day 5 lecture following section 2.5 of our textbook. So we're going to be continuing in chapter 2. Now we're only covering one textbook section in this video, and so it may be a little bit shorter. That's all right. It just means we may finish a little bit earlier, and then you'll be on your way for the day. In day 6, we're going to be finishing up chapter 2, and then that will wrap up our material for test 1. All right. Now I'll have more information for that as we um, get closer, and I will also send out an announcement on Canvas with more information about test 1. So that will be coming out in the next day or so. Okay, so let's go ahead and get started here as we are looking at section 2.5 of our textbook for day 5. So 2.5, what are we looking at? I'm going to switch to the board here, the whiteboard behind me, so I'll stop the screen share. So our concern, based off of last class, was that when we are studying these kinds of histograms, these frequency distributions that give us a kind of hill shape or mound shape, some kind of frequency distribution which looks like this, then we have in the middle, we have our median. Our mean should also be here in the middle where the data is clustered together in the middle, this central tendency. Highest peak, if it's the highest frequency, could also be the mode. So we have the median, mean, and mode all together here in the middle when we're dealing with this kind of hill shape or frequency distribution. All right. Now, as we continue, we're going to learn there are some special properties. In fact, any distribution that looks like this is called a normal distribution because, well, it's a um, it's a very commonly occurring, naturally occurring type of population distribution. Where one example we had from last class, we talked about height. We have most people are going to have a height around the average. Some people are going to be taller, some people are going to be shorter. And the taller you are, or the shorter you are, then that there's a lower frequency on these tail sides where that is less common or it's less frequent. But we're going to have a majority of people are going to be somewhere here in the middle. Another example of this would be like an IQ score. Most people have an average IQ of around 100. Now, some people might have an IQ which is higher than 100. Some people might have an IQ lower than 100. That's just another case of, in the general population, it's going to take this kind of hill shape where most people are going to be somewhere here in the middle. All right. You can also see this if we're talking about, people who are running a race for a mile, or if they're running a race for a marathon. Most people are probably going to be somewhere around the average race time, where some people are a little bit faster, some people are a little bit slower. If someone is faster or if someone's winning the race, they're ahead of everybody, then they're going to have they're going to have a shorter race time, right? The race time will be shorter, and there's only going to be a few people who are winning the race, who are at the front. Most of the pack, most of the people running the race are going to be somewhere in the middle of the pack, somewhere around the average race time. And then there's going to be some stragglers in the back who are going slower than the average. That would be another example of some kind of population of data, which has this kind of hill shape, where you have extremes above and below, but most of the data is going to be around the middle. Okay? Now, in 2.5, our concern with trying to study a set of population or population data, which looks like this, is a question of, okay, if maybe I just want to look at this region around the middle, right? I'm just going to focus on this middle region, and I want to ask the question, well, what percent of the population is in this region. Okay? And so this could be a possible question that we would want to answer. I know based on the picture that most of the population or a lot of the population is to be gathered here in the middle, but what percentage is that? How much of the population is that actually in reality? How do we estimate this, right? In order to do this, this was actually a pretty open question in the world of statistics, where even only just as recently as the 1800s, when mathematicians were working out this question, trying to answer, what percentage of a population is actually in the middle. All right. So the textbook highlights a guy named Chebyshev. Now I'm not going to write it on the board, but you can see in the textbook, Chebyshev was a mathematician in the 1800s, and he was working with this kind of question where, well, if I know the average, and so the average, we're going to use the Greek letter mu, right? That's supposed to be here in the middle, the Greek letter mu. And if I look at the average minus one standard deviation up to the average plus some standard deviation, because we know the standard deviation is a measurement for variability. If I look at one variation above or one variation below my average, well, how much does that account for? Is that a large portion? How can the variability help me to determine how much of the population I'm starting to capture as I look out some number of standard deviations away from the middle? Okay, so this was the question that Chebyshev was trying to answer. And he came up with a rule that was an approximation. This was a first attempt in the world of mathematics to answer this question. And he came up with this approximation, which is not exact, but it was a first try. Now on the board, and I apologize, I still need to get a new marker. Um, my marker, all right. I'm going to type this on the screen instead. Um, yeah, let's see. Let me let me do this, try to do this on the screen instead. Let me switch to, let's see. There's usually a whiteboard option. Here we go in Zoom. All right. It should be loading, hopefully. Okay, great. All right, great. Uh, oops. Okay. Let's see. It should be, do I need to share my screen? Okay, no, it's already sharing the whiteboard. Okay, so Chebyshev's rule. Let me put this here, and I'm going to call this C's rule. C for Chebyshev. And so, what did Chebyshev say? His rule stated that if you are considering some interval, so given an interval which is the mean plus or minus some number of standard deviations. So k times the standard deviation, whatever that is. And we'll do examples of this in a moment to get practice with this. So we would look at this interval where it was the mean, the average, which is our middle, right, of the normal distribution. And we're going to look at plus or minus a k number of standard deviations. So if k is 1, then that is plus or minus 1 standard deviation. If k is 2, oops, I misspelled interval. Let me fix that. Interval, okay. If k is 2, then that would be the average plus or minus 2 standard deviations, so on and so forth. All right. So we're creating this window based on how many standard deviations to the left and right of the middle am I looking? All right. And so what Chebyshev said, C's rule, he said that given this interval, we have that there is approximately um, at least for a formula here, yeah, 1 minus 1 divided by k raised to the second power. All right, and actually, you know what? Let me see if I can type that in as a formula. Text, can I switch it to a formula? Equation. Let me move it. Oops. Yeah. So given some interval, which is plus or minus a k number of standard deviations, then he had determined that there was at least 1 minus 1 divided by k raised to the second power. Oh, this whiteboard is kind of terrible. All right, I was hoping for better. Let me close that. That's not good. At least 1 minus 1 divided by k squared percent of the entire population is in that interval. Okay? So when I'm typing here, I'm using this caret symbol with k upper caret 2 to indicate that is k to the second power. If I were to write this as a formula or as an equation, this would be 1 minus 1 divided by k, kind of hard to do with my mouse here, raised to the second power. All right. And so this is what he said. So when k is 1, notably, what does this actually tell us? Well, it's an approximation. This was in our first attempt at answering this question. Unfortunately, approximations aren't always so good. So when k is 1, this would be 1 minus 1 divided by 1 squared. But 1 divided by 1 squared is just 1. So when k is 1, this percentage turns out to be just 0. When k equals 1, then at least 0% of the population is between whatever the average is minus, and I'll use SD when I'm talking about the standard deviation as a lower bound for my interval, and then mean, the average, plus the standard deviation. All right. Now, this statement doesn't really tell us that much, right? When we say the word at least, that means it could be any percentage greater than 0, which, okay, maybe we look at that and we're like, well, duh, at least there has to be some amount of the population, which is there in the middle. It's got to be bigger than 0. It can't be a negative percentage. So this rule is kind of useless when k is 1. But when we look at different k's, it does start to tell us something else. When k equals 2, well, now I'm looking at the average plus or minus. Oops, I didn't want to do that. Apologies. Here we go. When k equals 2, then at least, well, that would be 1 minus 1 divided by k squared. 2 raised to the second power is 4. This would be 1 minus 1/4, or in other words, 3/4. Now you put that in a calculator. 3/4 is equal to 0.75, which is a decimal, but as a percentage, that is 75%. Population is between, so we're looking at this interval, which is the average minus 2 times the standard deviation. That'd be 2 standard deviations below, up to the average plus 2 standard deviations above the average. All right. Now this is starting to tell us something. So according to Chebyshev, now again, this is giving us an at least. It's not telling us an exact approximation. Just like with 1 standard deviation. I know most of the population is supposed to be in the middle, or a lot of the population, but we don't have a percentage for that, at least not yet. But when k is 2, Chebyshev did prove that, well, in this case, plus or minus 2 standard deviations, that is at least 75% of the population. Now, because of the word at least, it could be a percentage greater, it could be a percentage higher, but it can't be a percentage lower than 75% if we're talking about the normal distribution. Okay, so that was what Chebyshev proved. He's trying to figure out what percentage is in there, and he starts with this lower bound. It's got to be at least 75% for plus or minus 2 standard deviations. But you can make k whatever you want here. K could be 3. K could be 4. You could even make k a decimal. What if when k is 2.5? Or if k is 1.5? Whatever k you want, plug it into the formula, and we can figure out at least what percent of the population has to be contained in that region. Okay? So this is what Chebyshev started with, what Chebyshev did for us. The same formula is also given in the textbook. This is called Rule 2.1. But on the very next page, we immediately get a better option. So I'm just going to switch back to the textbook screen here. So let's see. Let me close this whiteboard here for us. And I'm going to go back to the textbook. So I'm going to share my screen again. All right. What we next have is even better than Chebyshev's rule in some ways. This is called the empirical rule. Okay. Now, what does the empirical rule state or say? It says, again, just like we've been talking about, this normal distribution kind of shape, where we have this hill shape with the data. It says if you have the average in the middle, and then you look at 1 standard deviation below, 1 standard deviation above, that region is approximately 68%. So right away, this is telling us more information than Chebyshev had. 68% is approximately there in the middle, plus or minus 1 standard deviation from that middle. All right. If you go out 2 standard deviations, that's approximately 95% of the population. And if you go out 3 standard deviations, this is approximately 99.7, or essentially the entire population. I mean, 99.7, that's pretty darn close to 100%. All right. So using standard deviations as a measure for how far away from the middle are we looking, we start to see that variation, that variability can then indicate for us, well then, how far is my data really spread out? Where most of my data is going to be within 1 standard deviation or 2 standard deviations from the middle, from the average. Okay. And so we can do a lot with this kind of calculation. Let me hopefully maybe the marker will work. We'll try the marker again. And if it doesn't work, then we'll just come back to the textbook. So we have this picture, right? We've been talking about here. So a real world example where we could think about this normal distribution for population data would be if we're thinking about like IQ. How can I use the empirical rule to tell me information about IQ for different parts of the population? Well, the average IQ is 100 with the standard deviation of 15. Okay? Now, according to the empirical rule, if I'm looking at this normal distribution, I've got 100 here in the middle. Now, if I look out one standard deviation to the left and right, so that would be at 100 minus 15, that would be 85 as a lower bound, up to one standard deviation above. According to the empirical rule, this is 68%, oops, not 100, 115, one standard deviation above. So according to the empirical rule, 68% of the population has an IQ between 85 and 115. That's already a majority, right? 68%. That's a large proportion. But we can get more information from this. The empirical rule doesn't exactly say, but it's implied by the empirical rule. Recall from the last video, the average, or this median, is exactly in the middle, right? It's supposed to be symmetrical. Half of the data is to the left, half of the data is to the right. And so if this average is truly splitting everything in half, that means it's also splitting the 68 in half. And so I can get more information from this. What percentage of people, of the population, has an IQ between 100 and 115? Now I'm looking at a smaller window here, between 100 and 115. Well, half of 68, that is 34%. What percent of people have an IQ between 85 and 100? That's also 34%. So we can use the empirical rule to figure out some of these smaller regions to determine the percentage of the population which is represented by these regions. All right. If I go out 2 standard deviations, now I'm going out 2 standard deviations. This would be 100 minus 2 times 15, or in other words, that would be a lower bound of 70, up to 100 plus 2 times 15, that would give us 130. So now I'm looking at what percentage of people have an IQ between 70 and 130. Well, according to the empirical rule, this is 95% of the population. So even that's pretty high. I mean, that's almost everybody, right? That's 95%. Okay. But we can also figure out these smaller regions. If, again, the average is splitting everything in half, half of 95 would then be 47.5. So that means if it's split in half, 47.5 is represented from the average up to 2 standard deviations away. That would be up to 130. Well, if that's the case, this is 47.5. 34% of it is already right here, which means this region would be 13.5. So in this way, we can start to use the empirical rule to find out what percentage of the population is in these other intervals, which may be farther away from the middle. Okay? And if you go out 3 standard deviations, that's 99.7. Now, there's lots of questions we can ask about this now. We could say, if we're thinking about probability, if I pick a random person from the population, so let x, if this is a random variable or something that's randomly happening, let's say I'm doing a statistical study, and I'm going to pick a random person from the population. Let x be the IQ of a randomly selected person. And we could ask different questions now. I could say, well, what is the probability that this person has an IQ between 85 and 115? So I'm using P here to represent probability. I'm asking, what is the probability that this random person has an IQ in this region, well, that's just straight from the empirical rule. This is plus or minus 1 standard deviation. 68% of the population is there, so there's a 68% chance that that randomly picked person is in that region, right? That's 68%. Or, if that's as a decimal, I would write it as 0.68. Okay? But I can ask different questions also. I could say, well, what is the probability that this random person has an IQ greater than 115? Now, how do I answer this sort of question? Come back to the picture we're looking at. I'm looking at the probability that x is greater than 115. So what region is this? Well, I'm looking at the region which is to the left of 115. So this entire shaded piece, this tail end, to the right of 115. Okay. Now, the empirical rule doesn't exactly, or at least not right away, it doesn't tell me what this is, not at first glance, right? However, how can I find it using what we already know? Well, again, from like we said in the last video, the average is supposed to split this entire graph in half. Half of the graph is to the left, half of the graph is to the right. Well, if that's true, then that means this entire right side is supposed to be 50%, right? The entire right side is 50%. Well, then, if I'm trying to find this shaded region, all I have to do is subtract out the part that I don't want to count, and whatever is left over is the region I'm actually looking for. So in this case, if the entire right side is 50%, if I subtract out this 34%, it'll subtract out this piece that I don't want, then whatever's left over is what I'm looking for. So my answer would be the 50%. As a decimal, that's 0.5, minus the region that I don't want, which is 34%. We get that from the empirical rule, 0.34. And we find out, well, what percentage of the population would have an IQ greater than 115, or what's the probability of randomly selected person being in this region. This would then give us an answer of 0.16. So the odds that this randomly picked person has an IQ greater than 115 would be about 16%. Okay? So the empirical rule can tell us a lot of different things, answer a lot of different types of questions regarding probability and proportions, ratios, as we're looking at these different regions around a population of data which has a frequency distribution shaped like this hill shape, okay? Now, there are a few limitations here with the empirical rule. First of all, this only gives us information when we're looking at 1, 2, or 3 standard deviations away, right? Unlike Chebyshev's rule, if k were 2.5, if I'm looking at 2.5 standard deviations to the left or right, well, the empirical rule doesn't tell me anything about if I have a fractional number of standard deviations. The empirical rule, if we go back to the textbook here, so sharing my screen again from the textbook. If we go back to the textbook here, it only tells us about 1 standard deviation to the left and right, 2 standard deviations to the left and right, and 3 standard deviations to the left and right. So if I were to ask a different question, let's say, find the probability that a randomly picked person has an IQ greater than 105. Well, 105 is less than 1 standard deviation away, right? The empirical rule tells me nothing about that x value for 105. So later in the course, later after test 1, we're going to come back to this question as far as like, well, how do we answer these kinds of statistical proportion probability questions for different x's that are not exactly 1, 2, or 3 standard deviations. We don't know how to do that yet, but for now, we have this approximation method, which we can use when we're looking at numbers which are exactly 1, 2, or 3 standard deviations away. All right. So we can see this next example as kind of a first step into, well, what can we do with this? What intervals can I consider? So here they are doing an experiment with these 30 different rats who are running through a maze, and they're timing them in terms of how long does it take for them to get through the maze. Okay. Now, they are making some assumptions. First of all, we're assuming that this data for this rat race should be like a hill shape. It should be that normal distribution shape. Otherwise, I can't use the empirical rule, right? The empirical rule only applies to sets of data which look like this hill shape, okay? So we're assuming that it has a normal hill shape look to it. Now they've gone ahead and calculated the average and standard deviation for us. So fantastic, we don't have to do that. But we could if we wanted, and if we want extra practice, you could calculate the standard deviation and the average using those formulas from the day 4 lecture. All right, we're not going to do that for today, but that's where these numbers are coming from. So we can look at these intervals. According to the empirical rule, if I look at plus or minus 1 standard deviation, so I take the average minus 1 standard deviation, that's a lower bound, the average plus 1 standard deviation, that's an upper bound, and we have this interval from 1.54 up to 5.94. Now, according to the empirical rule, approximately, so I'm waving my hand here, it's an approximation, not an exact calculation, but approximately 68% of the population is supposed to be in that interval, right? But this is the kind of trial and error of statistics. The data here, this is not the entire population of rats that exist in the world, right? This is a sample of 30 rats, right? This is not the entire population of rats. This is a sample, a subset of the population that we're trying to approximate. So it's not the most accurate approximation, but it's an attempt on our part to approximate, to get a educated guess, all right? But in the reality, well, what percentage of this sample actually is in that interval between 1.54 up to 5.94? And if you look, you can count, there are actually 23 different rats that are in this interval, and 23 out of 30, that is approximately 77%. So that is different from the 68 percentage, right? This also highlights the empirical rule. It's not an exact science. This is just giving us an approximation for what is happening. But the numbers are a little different here, right? On one hand, maybe there's a problem of this sample might be too small. If I took a sample of 100 rats or 200 rats, again, think back to last class. With the central limit theorem, or sorry, not central limit theorem, um, going back to last class, when we're trying to approximate a population set of data, we need a large enough sample size for it to be a good approximation, right? If the sample size is too small, then my approximate average and my approximate standard deviation might not be that close to the true population, all right? Um, as we continue in the course, getting into later chapters towards the end of the class, we will talk about things like the central limit theorem. It was just popping into my head as I was talking about that the other day with another statistics class. But we're not there yet, right? We're not going to worry about that theorem just yet, but it will be coming later in the course, probably a little after test 2, actually. So it's a little ways down the road, but we'll get there later. The point we're just trying to make here is that the empirical rule, while it's an approximation, that's all it is, right? It's an attempt. It's an educated guess where if my sample size is a good approximation, then these percentages will be approximately true, all right? We can look at plus or minus 2 standard deviations. Well, then that's the average minus 2 times standard deviation, the average plus 2 standard deviations. We have this different interval now, and this contains 23 out of 30. That is 93% of the sample, which, okay, for plus or minus 2 standard deviations, the empirical rule says that should be approximately 95%. That's pretty close now to 93. Not a bad approximation. Okay? And then lastly, we can look at the interval, which is plus or minus 3 standard deviations. Okay? And so this is kind of a first example of how the empirical rule can be used to create these kinds of interval regions, which are approximating something we can observe about a population. All right. Now they give this other example with Chebyshev's rule, but I don't want to look at that for now. What I really want to focus on here is this car battery example, where we can now start to see how do we use statistics to answer questions in society. All right. So consider this problem. A manufacturer of automobile batteries claims that the average length of life for its grade A battery is 60 months, right? This sort of thing happens all the time in the real world. Some company, they have some product that they produce and they make a claim in their advertisement. They say, our product can do XYZ, right? And they claim, in this case, they claim this car battery can last for 60 months. They're claiming that's the average for the population of all their batteries. Now, is that true? Is it false? Are they maybe fudging the numbers a little bit? Are they lying a little bit to make us more impressed to buy their battery? Or is what they're claiming actually true and what they're advertising about it is correct? How do we find out? We have to do a statistical study. One idea could be to, well, let's buy a bunch of their batteries and we'll test them. How long do they last? When we test them, does it match what they claim? All right. This is a question we're going to see again later in the course, but this is kind of our first attempt at this sort of question. All right. Now, for this business, this car battery business, we also are told that they have a battery guarantee on the brand for 36 months. So they tell you, yeah, it'll last 60 months, but then their guarantee on it, their replacement for it, only lasts 36 months. So if it's after the 36 months, it's not a free replacement. If it's before the 36 months, they'll replace your battery for free. Okay. Now, we do have this assumption which is being made, told to us in the question. Suppose the standard deviation of the life length is known to be 10 months, and the frequency distribution of the life length data for these batteries is this mound shape, the hill shape, in which case I can use the empirical rule. Okay? But now we can ask some questions. Approximately, what percentage of the batteries will last more than 50 months, assuming the claim is true? Okay, well, they have this picture here down below for the empirical rule. We said earlier, plus or minus 2 standard deviations is 68%. That would be down to 50, up to 70, since that's plus or minus 1 standard deviation. Half of that to the left, half of that to the right. And so if I'm thinking about, well, what percentage of the batteries would be greater than 50, last longer than 50, that's everything to the right of 50 in this graph down here where my mouse is. All right. In which case, the percentage for that region is going to be this 34% on the left side plus the 50% on the right side. That means 84% of the batteries should last 50 months or longer if the average truly is 60. All right. So we can see that answer for part A. Now, if we look at part B, we have a different question now, What percentage of batteries will last less than 40 months? Since after all, their guarantee window is only up to 36 months, right? Is that actually a good guarantee? Well, if the average truly is 60 months, what percent of batteries will die before they reach 40 months, less than 40 months, assuming their claim is true? We'll now come back down to the picture. What percentage of the population of these batteries is less than 40%? Well, using the empirical rule, the entire left side, and I'll write this out in text format, the entire left side of the graph is 50%, right? We know that if their claim is true. We also know from the empirical rule that 95% of the data is between the average or the mean minus 2 times the standard deviation up to the average plus 2 times the standard deviation, right? So if I'm looking at this region from oops, let me back up. Is there an undo button? There is. 2 standard deviations below and 2 standard deviations above, then according to the empirical rule, that is 45%. This red region that I just drew on the screen, right? Well, or sorry, 95%. I'm getting ahead of myself. 95%. All right. But like we did on the whiteboard a moment ago, if I split this down the middle, this means 47.5% is from 40 up to the middle, the average, right? So 47.5% is now this region between 40 and 60. But what am I trying to answer? I'm trying to answer the question, what percentage of the population would have a lifespan of less than 40 months? This probability of X being less than 40. Well, the entire left side of this graph is 50%, minus the region we're not looking for, minus the 47.5 can tell me this tail piece I'm actually trying to find, and this is why in the picture they have 2.5% is written for this little tail region. So if I were to take a battery from this company, a randomly selected battery, the probability that that battery would die before 40 months would be 2.5%. Okay, which this makes sense for a business model. If the average lifespan for these batteries is actually 60 months and their claim is true, then the likelihood of this battery dying during the guarantee period would be super unlikely, and then their customers would never actually get to use the guarantee period. So it's a thing that the company can advertise and say, oh, look, we have this guarantee period, but it's unlikely to actually be used. And so they can look good for it, but then they're unlikely to actually lose money on it. That is, if their claim is true. Okay. Now, on the flip side, there's another question we can ask about this. And this is where part C comes into play. Let's say we go buy a battery and the battery dies after 37 months. So what happened? What does this mean? Well, there's two possibilities. One, the company was telling the truth. The average really is 60 months, and it's just bad luck. This one battery, which died at 37 months, it just so happens to be in this 2.5% region. Super unlikely, but just bad luck. It turns out that was one of their bad batteries that died early. All right. It could just be bad luck, but it's unlikely. There's only a 2.5% chance of having a battery die before 40 months. So what's the other possibility? Either the company is telling the truth, the average really is 60, or they maybe were lying a little bit to make their product look better, and maybe their average is actually smaller, is actually less than 60. Now, the information we have in this example, we don't know what the true average is. We don't know if they're lying or not. It could just be dumb luck that our battery died really early. We just don't know, right? How would we find out? Later in the course, this will be after test two, we'll look at ways for testing this sort of question. How can I find out if the company is actually telling the truth or not? We would need to collect a sample of our own, which is randomly generated, and then look at some statistical properties of that sample to be able to answer that type of question. We're not doing that yet, but for now, and with today's material, our attempt is just to begin working with, well, given some information or given some claim, what can we start to say approximately is represented in different regions away from the middle? That's all we're trying to do for today. We'll get to more complex questions later. All right. Let's see. So that fully answers part A, part B, and part C here. Or part C, I said out loud, right? What could we infer about the claim? It could be the claim is true and it was just bad luck. Or it could be that the claim was false and that the average is actually less than 60. But we don't know which is the case. We don't have enough information to be able to say more than that. All right. So this will wrap up section 2.5 for us. This was our last example. So let me clear the screen here. All right. They also give some step-by-step explanation of the same thing we did on the screen here that I was writing for us. And that is where 2.5 ends. Now, in the next video for the day 6 lecture, we will look at the rest of chapter 2, wrap up chapter 2 for our test 1, and then we will be ready for test 1 after that. All right. So let's go ahead and look at participation day 5. So here we're given the question, given the below data results, approximately what range of AE scores accounts for 68% of the female data using the empirical rule? So this data, this is a printout from some sort of sample that had been collected where we have these scores for women, we have these scores for men, we have the N, which is the sample size, how many women were in the data, how many men were in the data, what was the average score, and what was their standard deviation. Now, according to the empirical rule, plus or minus one standard deviation, so the average minus one standard deviation up to the average plus one standard deviation, this region is approximately 68% of the population. So what can we do here? Well, we have the average for women here as we're trying to create an approximation for an interval for women in this data for these AE scores. The average was 17.05. The standard deviation is 4.757. Okay, so we have that. So then 68% is the average minus a standard deviation up to the average plus one standard deviation. So this would be 17.05 minus 4.757 up to 17.05 plus 4.757. Okay. And from here, we go to a calculator to get our answer. 68% of women have AE scores in what interval range? Well, we go to a calculator, and we have 17.05 minus 4.757, which would give us 12.293 up to an upper bound of 17.05 plus 4.757, we get 21.807. So for our answer today, what percentage of women have an AE score between, or what, we're trying to answer the question, 68% of women in the AE scores for this data are approximately in what interval? That interval is from 12.293 up to 21.807. And so that is our answer for today's participation question. All right. If you have other questions regarding this material or homework questions or anything else going on in the class, please feel free to email me, come by office hours, let me know what your concerns may be. Otherwise, that's all for this video. I wish you the best of luck, and I hope you have a great day. All right. Bye for now. I will see you in the next video.